Tonight on The Future of Everything, we've got 3i Atlas updates and maybe even our best shot yet to clearly see the third interstellar object ever detected passing through our solar system. But let's just rewind real fast for a second here, because this thing has been on our radar only for about a few months. Since then, things have gotten very, very interesting. According to astronomers, 3i Atlas has all kinds of surprises. We've only seen a handful of blurry shots that look like a tail is kind of starting to form. There's the unusual chemical signatures. It's producing way more nickel than iron, and scientists don't really know why. And when it comes to size, some estimates say it's about 3 miles wide. In comparison, Manhattan, it's only about 2 miles wide, and that is at its widest point.
There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe. While many think it's just a comet, some theorizing a possible alien origin due to a few curious characteristics.
The peculiar thing about it is that it's moving along a trajectory that is very special.
October 21st, 2025. Just as 3i Atlas hits peak solar heat, when the secrets of our third known interstellar visitor should finally be exposed, Earth goes blind. For 6 critical weeks, every telescope falls useless in the blinding glare of the sun. This isn't just an astronomer's nightmare. This exact blackout window would be the perfect cover for anything wanting to change course unseen. But right before the countdown to 3i Atlas changing its course began, shockwaves hit the scientific world. James Webb measured a carbon dioxide to water ratio 8 times higher than any comet ever seen. Mars flybys found persistent asymmetry, and KK's nickel maps revealed chemistry that shouldn't exist. What aren't we seeing while the sky goes dark? And what will decide if this story ends in December with routine comet science or a fundamental rewrite of everything we know? Solar glare is absolute. When 3i Atlas crosses behind the sun from Earth's perspective, every instrument, optical, infrared, radar, hits a wall nearly 1 million miles thick. On October 21st, the geometry locks in. New moon, superior conjunction, and the object's closest approach to the sun just 8 days away. For 6 weeks, the sky is off limits. This isn't a technical glitch or a bureaucratic delay. It's physics. The sun's disk swallows the line of sight. Even the most sensitive telescopes, tuned to pick up faint signatures from the edge of the solar system, can't punch through that kind of radiance. Not in visible light, not in radio, not even with the most advanced thermal images. The blackout is total. Numbers matter here. A conjunction, the separation between 3i Atlas and the sun, as seen from Earth, drops under 1 degree. That's less than 2 solar diameters. The object's own signal, already faint, gets drowned in the solar corona, a plasma sea hotter than 1 million degrees. The glare zone stretches 965,000 miles. Any attempt to observe through it is like trying to spot a candle behind a floodlight from the far end of a football field. Even radar, which can sometimes ping objects close to the sun, loses coherence in this soup of charged particles and magnetic chaos. Mission planners know the calendar by heart. October 21st, blackout begins. October 29th, perihelion, maximum solar heating. The moment a comet's secrets usually spill out in gas and dust. But this time, Earth is blind exactly when the object is most vulnerable, most likely to show its true nature. No direct images, no spectra, not even a hint of reflected sunlight. For 6 weeks, the only thing coming from 3i Atlas is silence. Why does this matter? Any change, outgassing, fragmentation, even a course correction, would happen out of view. The timing isn't just inconvenient, it's perfect cover. If something wanted to alter its path without being caught, this is the window. The blackout isn't just an observational gap. It's a test of trust in physics, in models, in the limits of what light can tell us. When the object finally re-emerges in December, every prediction, every theory, every bet made during the blind interval will be put to the test. Until then, the countdown ticks on, and the sky stays dark. Receipts matter. Before the blackout, every major observatory raced to pin down what made 3i Atlas so strange. The James Webb Space Telescope, under Dr. Melissa Jiang's emergency request, caught the object on September 18th. Its infrared spectrum delivered a shock. Carbon dioxide to water vapor, 8.1. That's not a typo. In normal comets, water dominates. Here, the ratio is flipped and then some, an outlier by 6 standard deviations. JWST flagged strong carbon dioxide, moderate carbon monoxide, and traces of carbonyl sulfide. The isotope ratios looked solar, but nothing else about the chemistry fit the playbook. Internal NASA chat logs show how close this data came to being embargoed. Zhang's team argued that missing the solar heating peak would leave the field in the dark, maybe forever. Meanwhile, Japan's Keck Observatory mapped the coma in August and September. Nickel lines glowed bright. Iron lines barely registered. The outgassing wasn't random. Gas and dust streamed sunward, forming a narrow asymmetric plume. Peer reviewers hesitated, worried the nickel anomaly might be a mirage or a calibration error. But the reduction pipeline held up. No artifact, no instrument ghosting. The nickel was real, the iron was missing, and the geometry was lopsided. The coma stretched nearly 6,000 kilometers in narrowband images. Mass loss rates landed at about 150. Guess, water production trailed at just 40 keys. Another hint that something about this object's chemistry and its engine runs outside the norm. Hubble's July 2nd images confirmed what ground telescopes suspected. A broad, smooth, teardrop-shaped coma, rare even among solar system comets. No sharp jets, no ragged edges, just a steady enveloping glow. The nucleus itself stayed hidden, but light curve analysis from Rubin Observatory's pre-discovery images on June 21st let teams estimate the size, 5 to 6 kilometers across, spinning slowly, almost imperceptibly. No wild brightness swings, no fast rotation, just a big, cold, quiet traveler. On October 3rd, Mars assets took their shot. ESA's Mars Express and the Trace Gas Orbiter, directed by Nicholas Thomas's CASSIS team, caught the object as it passed, 0.19 astronomical units from Mars. The coma was faint but active, outgassing steadily toward the Sun. The images and spectra showed Sun-facing activity that persisted right up to blackout. Internal ESA logs describe a tense debate over when to release the data, but transparency won out. Public confirmation landed on October 8th. The geometry of the outflow, the chemistry, the light, all pointed to an object that doesn't follow the usual rules. Each dataset is a baseline. Carbon dioxide swamps water. Nickel outpaces iron. The coma's shape is smooth, sunward and stable. The nucleus is big, slow, and quiet. Mars flyby data confirms the activity is real, not a trick of Earth's atmosphere or telescope software. These are the fingerprints to watch. When the object reemerges in December, any change, any deviation from these receipts will speak volumes. 3 interstellar objects, that's the entire catalog. Out of trillions of rocks and ice balls drifting through the galaxy, only 3 have ever crossed the Sun's front porch while humans were watching. The first, oumuamua, shot through at a steep angle, never even grazed a planet. Borisov II swept in fast, high above the ecliptic. Now, 3I Atlas arrives on a path that seems almost scripted, just 5 degrees off the solar system's main plane, threading the planetary lanes like it belongs here. Odds of that alignment? About 1 in 20,000. Not impossible, but not the kind of number you see by chance every day. Here's how those odds stack up. Most interstellar objects should arrive at random angles, scattered across the sky. The ecliptic, the flat disc-shaped zone where planets orbit, is a narrow band. Only a small slice of space lines up with it. For an interstellar visitor to slip in along that plane, and at such a low inclination, takes more than a roll of cosmic dice. It raises eyebrows but not alarms, at least not yet. Astronomers warn against reading too much into a single case. With only 3 ISOs on record, every new arrival feels like an outlier. Small sample statistics play tricks. If the next dozen interstellar comets show similar alignments, then the story changes. For now, it's a statistical blip, not a conspiracy. Trajectory isn't just about angle. The path 3I Atlas follows brings it within striking distance of multiple planets. Mars in October, Venus in November, Jupiter next spring. Each close pass offers a chance for gravity to tug, to nudge the orbit, to reveal any deviation from prediction. That's why pre-blackout astrometry matters so much. Every data point, every position logged by Rubin, Hubble, Mars Express sets a baseline. When the object reappears after conjunction, even the smallest mismatch, a few arc seconds off, could mean something changed. Maybe a jet of gas, maybe a fragment broke loose, or as some speculate, something less natural. But before jumping to conclusions, the math demands caution. The solar system is a busy place, and the ecliptic is a natural highway. Even rare events happen, given enough time and enough objects. What matters isn't just the rarity, but whether the trajectory stays true. December's reappearance becomes the referee. If the orbit matches every prediction, the improbable path becomes just another data point in a growing record. If it doesn't, the search for explanations begins in earnest. Until then, the numbers hold their breath, waiting for the next move. October's sky was anything but quiet. Solar physicists tracked a surge in activity as 3 coronal mass ejections, CMEs, launched from the Sun in October. Meanwhile, the world below watched the auroras stretch far south, green curtains over Kansas, pink glows in France. Online, theories multiplied as quickly as the geomagnetic indices. Some claimed the surge triggered earthquakes, while others insisted the blackout around 3I Atlas was no accident. But professional bulletins drew a hard line. The true blackout was geometric, a matter of alignment, not a failure of hardware or a solar conspiracy. The sun's glare, not its flares, sealed the window on observation. Still, the timing fed speculation. Isabel Ruiz, an amateur comet tracker from Madrid, posted her tally, 17 green comets at once. Her viral thread, boosted by spectacular aurora photos and a list of every active comet, set off a moderation scramble in astronomy forums. The actual count, 4 bright green comets, Lemon, Swan, K1, and 3I Atlas, was dramatic, but not unprecedented. The clustering, experts explained, was a trick of the Rubin era. With the Vera Rubin Observatory's nightly sweeps, faint comets that once slipped by unnoticed now show up in droves. Detection bias, not cosmic choreography. Ruiz's enthusiasm didn't stop there. She flagged a faint glow trailing 3I Atlas in amateur images, maybe a fragment, maybe a companion. Professionals urged caution. Without astrometric confirmation, any claim of fragments or engineered buffers remains just that, a claim. The Minor Planet Center and JPL logged every credible report, holding the line for December's imaging window. Only then, when the object reemerges from behind the sun, will the fragment question be settled. The October space weather spike added noise to already complex models. Solar wind conditions changed hour by hour, complicating predictions for dust and gas behavior around the object. But no instrument failure, no data blackout, no sudden loss of control, just the relentless push and pull of charged particles, the routine chaos of solar maximum. For modelers, every CME and geomagnetic ripple became another variable to factor in, another source of uncertainty for December's critical test. In the end, the surge was real, but not the culprit. The blackout belonged to celestial mechanics. The crowd's excitement, the viral posts, the fragment rumors, they're all part of the story. But the science holds its ground. The real test waits for the sky to clear, for new data to break the silence. Avibe calls it the solar Earth scenario. Imagine 3I Atlas as more than a comet, a probe capable of burning its engines at perihelion, using the sun's gravity to change course. If that's real, the maneuver would happen in perfect darkness, hidden behind the sun, right when Earth can't watch. The only proof would come after, a sudden, measurable deviation in the object's path once it reemerges in December. The test is brutal in its simplicity. Every major observatory, Rubin, Hubble, JWST, and ground arrays, will track the object's position to within 10 milliseconds. That's the width of a coin seen from 1,000 kilometers away. If 3I Atlas follows its predicted orbit, the story ends with physics as usual, a noisy, exotic comet, nothing more. But if the path jumps by even 100 milliarcseconds, equivalent to a 10 ms velocity change, cometary models can't explain it. Outgassing, the usual culprit, is too weak and too slow. Only a sudden, deliberate force could fit the data. Mainstream astronomers are careful. They point to the chaos of comet activity, wild jets and uneven mass loss that can nudge a nucleus off course. But the precision of this test leaves little room for ambiguity. December becomes a binary. Either the numbers line up, or something unaccounted for has happened. Avibe's hypothesis hangs on that razor's edge. Astrometry, not speculation, will decide the outcome. Every pixel, every timestamp, every arcsecond matters. The countdown isn't just to a reappearance. It's to a verdict. Rubin Observatory rewrites the odds. Before its full survey cadence, interstellar objects were rare events, one every few years, if that. Now, with nightly sweeps and automated pipelines, the expectation shifts from anecdote to archive, dozens of interstellar objects per year. Not a trickle, a flood. Each new arrival, logged with precise timing, color, and motion, builds a dataset that turns outliers into statistics. The next time a hyperbolic visitor threads the ecliptic, it won't be a solitary headline. It'll be one of many, cross-checked against a growing catalog. This is the future of interstellar object science. Every orbit, every outgassing ratio, every fragment trail gets measured, compared, and stacked. Patterns that once looked suspicious, like low-inclination entries or close planetary passes, become testable, not just debated. The same goes for chemistry. 6 sigma carbon dioxide ratios, nickel-rich coma, teardrop-shaped glows. With enough samples, the line between rare and routine sharpens. The discipline moves from case studies to population analysis. Rubin's reach isn't just about numbers. It's about timing. Early detection means more lead time for space-based assets, more chances to catch activity before and after solar heating. Coordinated campaigns, Mars orbiters, Hubble, James Webb Space Telescope, ground networks can now pivot faster, track more objects, and fill in the gaps left by geometry or weather. What was once a scramble becomes a system. The mystery of 3i Atlas, whether anomaly or new archetype, is already part of a larger shift. The floodgates are open. The next verdict won't be the last. The December reemergence will test whether its orbit matches predictions or shows unexplained changes. If the trajectory holds, it supports a natural, if unusual, comet. Any deviation could demand new explanations and urgent follow-up. As surveys like Vera Rubin prepare to find dozens of interstellar visitors each year, the current blackout underscores both our advances and our limits. For now, 3i Atlas stands as a case defined by hard evidence, open questions, and the promise of answers just out of sight.